Hi, my name is Ruben Janssens. I'm here to present the Ghent University submission to the ERR at HRI challenge. I'm really sorry that I can't be there in person today, but I hope you're having a wonderful time nonetheless. So I will present the work that we did in the challenge, and we is me with my co-authors Eva Verhelst and Mathieu de Koster. So just to recap, you've probably heard this many times before already, but what is this challenge that we're working with? What is this data? So this data consists of about 10 hours of recordings of human-robot interactions. And these interactions contain mistakes, mistakes that we call either robot mistakes, user awkwardness, or interaction rupture when one of the two previous ones is happening. And of those 10 hours, about 10% of those are mistakes. Now, we don't get the raw like the raw videos or recordings of the interactions, but instead we got extracted features about the facial expressions, the body pose, and the speech. And those were extracted with open face, open pose, and open smile. We got those at different frame rates as well, either 30 or 100 frames per second. And then we got the three labels over the entire interaction of whether or not there is a robot mistake. So using this data, we built a few models that aim to predict when one of those three phenomena was happening. And first I will explain a bit how we did the data pre-processing, then I'll go more in detail on the metrics that we used, of course also the models that we have tested and designed, and then I will finish with the results and some conclusions and future work. So for the data pre-processing, we did similar to what the organizers did in the code that they provided. We normalized each feature so that it has a mean value of 0 and a variance of 1 over the entire training set. And then we sampled each of the input features and also the ground truth labels at 30 frames per second. So it would be the same for each of the features and the output labels. And then finally, we also provided context windows for each frames. So that means that in our pre-processed dataset, we have provided the previous n input value frames for each frame. And that parameter n we call the sequence length, and that's an important one that we will be fine-tuning for each of the different models. And then how do we evaluate our models? We are using the metrics that were provided by the organizers as well, of course. So that's accuracy, precision, recall, and the F1 score. Now for the F1 score, the version of this that is used by the organizers is the macro F1 score. So that means that we calculate the F1 score with 0 as a positive label and 1 as a positive label. And in this, the 1 is the one that corresponds to when the mistake has actually happened. Now we also calculated the micro F1 score, and that is the one that's only calculated for 1 as the positive label, so when there's a mistake. And we do that in order to penalize models that will only predict the majority class, or that will much more predict the majority class than is warranted by the proportion in the data. Because as the dataset is highly imbalanced, with 90% of the data corresponding to no mistake, models are tempted to only predict that there's no mistake. And using the micro F1 score kind of combats this phenomenon. And then finally, also we looked at applying a tolerance of 1 frame to each of those metrics, as also provided in the code of the organizers. But this usually had only a very small effect, so we focused on the metrics without tolerance. So which models did we test? We started with creating the 2 baseline models provided by the organizers, and then we tried different architectures. First, simple dense neural networks. Then we tried to get the models to predict more coarse-grained predictions. We looked also at using convolutional neural networks and embedding layers, and finally at good old-fashioned simple random forests. So first of all, recreating the baseline models. There were 2 baseline architectures, either using a single layer neural network with the gated recurrent unit architecture, or using a bidirectional LSTM layer, also a single layer neural network. And then for both of these architectures, the starting parameters were a hidden feature size of 128 and a dropout layer with dropout probability of 0.2. And the first problem that we really saw was really fast overfitting, as you can see on the graphs to the right. especially using the default learning rate of 1e minus 4, the validation loss just goes up immediately and very fast. So we also tried lower learning rates, and as expected, that kind of slowed down this phenomenon, with the validation loss first decreasing, which is what we actually want, and then slowly increasing again. Then we also looked at increasing the sequence length to longer values than the default of 5, because then the model would have more information about the past of the interaction, because the phenomena like robot mistake, interaction rupture, and user awkwardness actually take place over much longer time scales than 5 frames. So we tested to 5, 20, 40, and 60 frames for sequence length, but that only had a relatively small effect. Then, as I already mentioned, a problem is that the models tend to really be biased towards the majority label and predict in an imbalanced way. So we also tried out a weighted loss, which weights the loss for the two classes in such a way to try to force the model to predict the minority class more. And this does increase the micro F1 score, but it is lower the macro F1 score and the accuracy. And finally, also to combat overfitting, we tried increasing the drop-out probability to 0.4, and that has a slight positive effect. But all of these interventions only had a small effect, so we looked into more drastic changes to these models. So first of all, we tried dense neural networks, because the two architectures that we tried before are relatively complex and tend to overfit. So we also tried simpler models, meaning very simple dense neural networks. Now, because these models are not designed to process temporal, like a temporal dimension, like the gated recurrent unit and the LSTM are, instead we take the context window, so for example the sequence length of 5 frames, and we average the input features over that sequence length. And then using that technique, we tried 4 interactions. First, a very simple single layer, so a single linear dense layer with 128 hidden features. Then we tried 2 layers with a ReLU activation function in between. We also tried 2 layers, but with only providing the last frame instead of the 5 frames of context, but then averaged. And then we also increased the model size to 512 hidden features. But all these interventions and also trying out different hidden feature sizes don't make the model performance go above the kind of plateau macro F1 score and accuracies that we found in the previous experiments as well. So we tried different interventions. And first of all, what we actually see if we look at the predictions that this model actually makes is that it predicts very fine timescales. So you see that on the x-axis we see the number of seconds in the interaction, and we see that the model actually predicts for very short time spans, while the ground truth is much more coarsely grained. So we looked at how to kind of force the model to predict more coarse-grained predictions as well. First of all, we used the models that we already made based on the baseline models, and we applied a low-pass filter on the model output. So that means that we take a sliding window over the model's predictions, and we take the median of the predictions that the model has made. We tried out window sizes from 10 to 190, and we saw that with a window size of 140, the accuracy of the model goes up a little bit, also the precision, but it didn't have a really big impact. So instead we tried to combat this on the training stage. And to do that, we partitioned the data in non-overlapping sequences that were as long as a sequence length. So for example, partition the data in sequences of 5 frames, and then we take the majority label over those 5 frames and let the model only predict that one single value. So instead of predicting one value for each frame using the 30 frames per second, we let it predict only one value for every 5 frames or 20 frames or 40 frames. So we tried out these different sequence lengths, and we also tried tuning the learning rates using a weighted or unweighted loss, and so on. And what we see is that we still cannot cannot get beyond this accuracy and micro F1 score plateau that I mentioned before. But we do see, if we look at the micro F1 score, that these scores are increasing. And those you can also see on the graph on the right, on the bottom right. Now, that kind of tells us that the model is learning more detailed patterns, and it's not just predicting the majority class anymore. But what we do see is that there is an inverse correlation between the macro and the micro F1 score. So that's a bit annoying since we're trying to optimize the macro F1 score and the accuracy for the challenge, of course. What we also do see is that giving a longer sequence length here does lead to a higher micro F1 score, which is what we expected, but it takes longer for the model to train, and that's why we're training for up to 200 epochs instead of just 100. Now, if we then try to change the architecture, not just the training data, to make the model predict in a more coarse-grained way, we look at convolutional neural networks, since those they're usually used to downsample data on a spatial dimension. Take, for example, an image that has 124 by 124 pictures. Convolutional neural networks will kind of downsample that to a lower dimensionality, but you can also use that for the time dimensionality, as has been done by researchers before as well. So we use that here, and also what we do is we apply an embedding layer to reduce the inputs dimensionality, because we have relatively high dimensional inputs features, but those are also quite correlated in some cases, so we try to optimize the model by using an embedding layer. So we try out 3 different architectures, first using a linear layer that acts as this embedding layer, and then a GRU at the end. We also tried just using the convolutional neural network and with a GRU, and then we tuned the kernel size for these convolutional neural network layers. And then we also tried the combination of the 2 of them, an embedding layer, a CNN, and a GRU. And here we also try using both a weighted and an unweighted training loss. And as you can see to the right, this does help to improve the micro F1 score. But again, there's this balance between, there's trade-off between the macro and micro F1 scores. And then finally, the last model that we tried is a random forest, so a non-neural model that has been shown to be robust for smaller data sets. There's 3 settings that we have to look at for random forests, either the number of decision trees, then also the number of samples used when fitting each tree, and finally the minimal samples of the minimum number of samples in each leaf of each decision tree. So we test out different values for those settings. We also look at using balanced class weights, so that's a bit like the weighted loss for the neural networks, but that does not improve performance. And also because random forests are not used, they're not made to process temporal data, we have to engineer this a little bit as well. So we try out a few different options here. Either we just provide the input features for the last frame. Second approach is averaging these input features over the sequence length. And then third, giving the values for each and every frame in that sequence length. And then finally, we engineer an approach a little bit, and we provide the first, middle, and last frames input values, but then also the mean over that entire sequence and the mean over the last half of the sequence. And this should give the model a little bit more information. And then, with all of these different combinations, we had to choose which models to submit to the challenge. So for each of the tasks, we submitted first the model that got the highest accuracy and macro F1 score, since those are, of course, the 2 metrics that are also used by the challenge. Second of all, we also submitted the models that had the highest micro F1 score. And finally, we also chose models that had a good balance between the accuracy, macro, and micro F1 score. So because we tested out different types of models for different subtasks, that leads to the models that you see on the left. And then when we look at which models performed the best on the test data, we see that for the robot mistake and the interaction rupture tasks, it's the model that had the best balance between the macro F1 score accuracy and micro F1 score. Those perform the best on the average of all the metrics on the test data. So that corresponds for the interaction rupture to the random forest, but for the robot mistake to the model using an embedding layer and a CNN, and then the GRU layer as well. So that kind of shows us that optimizing just for the micro F1 score, that doesn't work, since of course we're not using that for the challenge. But optimizing for this balance does seem to be ideal, because then we're also kind of forcing the models to learn more detailed patterns than just predicting the majority class. But it also is clear that the 3 subtasks each require a different approach, since, for example, for the user awkwardness, the random forest doesn't help like it does for the interaction rupture. And then finally, summarizing everything that we did, we saw 3 main challenges here in our work on this challenge. First of all, models tended to really overfit very quickly, since this is of course a relatively small data set. Second of all, the labels that we have, the ground truth labels, are much more coarse-grained than the input features, which are at 30 or even 100 frames per second. And we tried out different hyperparameter settings and different model architectures in order to let the models predict more coarse-grainedly, just like the ground truth is. And then third, the data set is quite unbalanced, since only 10% of the data corresponds to the minority class, to robot mistakes. So that means that we have to carefully choose our metrics and our training procedures to make sure that we have models that can handle this. And we saw that optimizing for both the macro and micro F1 scores works. Also that random forests remain powerful for small data sets like this, but also that the 3 subtasks in this challenge are quite different. And it seems that there is some different structure in the data for these 3 subtasks. And what we think would still be really interesting for future work is to analyze the individual modalities and features more. We did not do that. We more explored different model architectures and this temporal aspect. Also, we were not able to look at the raw data, of course, because we only got the anonymized data, but that would be very helpful as well. And finally, it might be promising as well to use transfer learning from other effective computing tasks, or using embeddings that were pre-trained on other data sets. And that is it. I hope that was interesting, and feel free to contact me or my co-authors Eva and Mathieu if you have any further questions.